Welcome to another explainer. Today, we're unpacking a literal battle of man versus nature, how engineers pulled off the impossible to build the absolute tallest structure on Earth. When you look at the Burj Khalifa dominating the Dubai skyline, it's so easy to just marvel at how it looks. But reaching a height like that wasn't just about stacking materials. It was a full-on war against invisible forces. George Efstathio, the managing architect over at SOM, really hits the nail on the head here. He points out that the sheer height wasn't actually the main obstacle. The true adversaries in this engineering marvel were gravity constantly pulling everything down, the extreme desert heat threatening to literally destroy materials before they could even be used, and, of course, severe, unpredictable high-altitude wind. So here is our battle plan for this explainer. We're going to systematically deconstruct how human ingenuity defeated these challenges. We'll cover define the elements, securing the massive foundation, pumping ice to the sky, taming the wind, and finally, looking at the blueprint for the future. Let's get right into it. Part 1. Define the elements, the ultimate architectural battleground. Let's really wrap our heads around the sheer scale we're dealing with here. 828 meters. Think about that for a second. That is over half a mile straight up into the sky. When you thrust a massive structure into an environment like that, standard engineering simply fails. At this altitude, the everyday rules of physics start testing the absolute limits of concrete, steel, and honestly, human endurance. Which brings us to part 2, securing the massive foundation, or the ground battle. Because before you can go up, you absolutely have to go down. To keep this 828-meter giant from just sinking into the shifting desert sand, they couldn't just pour standard concrete. They engineered a massive 3.7-meter thick solid piled raft using 12,500 cubic meters of self-consolidating concrete. And that's entirely supported by bored piles plunging 50 meters deep into the earth. But here's the wild part. The real hidden danger was actually the groundwater. It's incredibly corrosive down there, packed with 3 times the sulfates and chlorides of normal seawater. So to stop the steel reinforcement from literally dissolving in the earth, they had to wire up a specialized cathodic protection system. They essentially run a mild electrical current through the foundation just to fend off rust. Talk about fighting for every inch. Okay, moving on to part 3, pumping ice to the sky. This is where they had to defeat both the heat and the relentless pull of gravity. In Dubai, summer shade temperatures regularly blow past 122 degrees Fahrenheit or 50 degrees Celsius. If you tried mixing normal concrete in that kind of heat, it'd be completely useless. It would dry out, crack, and fail long before it ever left the ground. This environment demanded a totally revolutionized approach to materials. To survive this, engineers invented a remarkably strict, high-performance concrete protocol. To keep the concrete temperature below 90 degrees Fahrenheit, they didn't just use cold water. They were literally mixing the concrete with crushed flake ice, basically pumping an ice slush. On top of that, pouring was restricted strictly to the dead of night, between 1 a.m. and 5 a.m., and their quality control was absolutely ruthless. Any truck taking over 90 minutes to arrive was completely rejected, sent away. Then, to defeat gravity, they had to pump this specialized mix at a staggering 200 bars of pressure. That's nearly 3,000 pounds per square inch. In fact, engineers used the world's most powerful concrete pumps to push this icy mixture a record-breaking 600 meters straight up. That is nearly half a mile of vertical pumping. And they had to achieve that delivery in under 30 minutes so the mixture wouldn't separate or set inside those massive steel pipes. Just imagine the logistics required for this. You're pushing heavy, wet rock half a mile into the sky, in the pitch black of night, racing against the clock before the desert sun rises and literally bakes it. It's just a breathtaking testament to human construction and material science. Which takes us to part 4, taming the wind. As they pushed higher and higher, a new and even deadlier natural enemy took over. Now, you might think the weight of the building itself is the biggest issue, right? It's a common misconception. But at extreme skyscraper heights, the dominant threat is neither the dead load nor the live load of the building. It is the wind load. And history has taught us some pretty harsh lessons here. Earlier structures like the John Hancock Tower and the Citicorp Center faced massive crises and near collapses simply because wind forces were initially misunderstood. The real danger comes from a terrifying phenomenon called vortex shedding. When wind hits a tall, slender building, it doesn't just flow smoothly around it. It peels off the corners, creating alternating whirlwinds.
These vortices can violently pull the building from side to side. If those whirlwinds happen to match the building's natural frequency, the resulting resonance could cause catastrophic swaying.
To defeat this, the project brought in wind engineering expert Peter Irwin. He and his team conducted over 70 different wind tunnel tests on scale models, and they used those results to fundamentally reshape the building. Instead of a uniform block, they designed a U shape that steps back unevenly as it rises, spiraling upward. This definitely wasn't just for aesthetics. It was a literal survival mechanism. By softening the corners of the outer buttresses and utilizing a spiraling motion that narrows the tower at higher levels, they totally changed how the wind interacts with the surface. They even went as far as reorienting the entire tower relative to Dubai's prevailing winds. In total, they created 24 different floor plates. Because the shape is constantly changing as it ascends, the wind can never really get organized. They literally confused the wind so it couldn't lock into a destructive rhythm. Unlike a standard block skyscraper, where a uniform shape allows those dangerous wind vortices to perfectly align and create resonance, the Burj Khalifa's asymmetric spiraling profile acts like a giant spoiler. By breaking up the cross forces, the structure remains incredibly stable, easily withstanding terrifying gusts of up to 240 kilometers per hour. Absolutely wild. Finally, part 5, Blueprint for the Future. Because the engineering marvel definitely didn't stop once the concrete dried and the steel spire was placed. You see, a building of this insane scale actually moves. It expands and contracts with the sun's heat, it settles into the earth, and it sways slightly in the wind. To manage this, engineers used cutting-edge GPS and Leica geosystem technology to keep the tower perfectly aligned as it grew. It was constantly monitored to ensure its center of gravity stayed exactly where it needed to be. And that monitoring didn't just stop when construction ended. Even today, the Burj Khalifa features an extensive structural health monitoring program. We're talking real-time GPS tracking of the building's tilt, continuous foundation settlement monitoring, strain sensors embedded right in the vertical megacolumns, and fatigue tracking all the way up at the pinnacle. The building essentially has its own central nervous system. This makes the Burj a living, breathing laboratory, providing data that is going to define the future of architecture. So, by rethinking concrete, mastering the wind, and using unprecedented technology, we conquered the shifting earth, the baking heat, and the violent skies to reach 828 meters. We won this particular battle against nature. But as our cities grow more crowded and materials become even more advanced, where do the limits of human ambition actually end? How much higher can we safely go? It's something to think about. Thanks for joining me for this explainer, and I'll catch you next time as we continue to unpack the fascinating world around us.